Okay, so I have a set of notes kind of set up similarly to the last one, but this is going to be specific for projectiles fired at angles. So there's the two formulas that we just derived, right? And just another little note about them. We still don't need to put initial or final on the VX, because still, even though we're shooting at an angle, something's still true about the horizontal velocity. It's what the whole time? Constant. So whatever this Vx is that we find through this equation, if it comes out to be 10 meters per second, that'll be 10 meters per second until it hits something, as long as there's nothing speeding up or slowing it down, like significant air resistance on the horizontal axis. But the y one we get from that formula is truly just initial, because as soon as it's shot upward on the way up vertically, what can we say about its velocity? When something goes up, it does what? It will come down, but on the way up, what can we say about its velocity? It'll slow down and come to a stop, and then on the way down, it'll do what? Increase. So it's always changing, right? So this is truly just the initial one. This is going to be constant the whole time, like always. There's some important features I have noted here, and we're going to note them on the diagram below. And these are exactly the same ideas as free fall, but it just happens to be moving this way at the same time. All right, so we said it free fall one more time. When we just threw something straight up before it came back down, again, what did it have to do? Stop. Well, when I throw something like this, before it comes back down on the y-axis, it has to do what? Stop. Now, it doesn't stop this way. It never stops this way. But vertically speaking, it has to stop until it comes back down, right? So we could always say that the V at the peak is 0, and we could still do similar things that we did in free fall. Remember how, like, if it helped me more, I could use the way down instead of the way up? I could do that here. So when we say the y, the 0 at the top, it depends on how we view it, which V that is. On the way up, if we go from where it was shot to that point, that would be Vy final, right? But we could also view on the way down, start initial here and final here, right? So we could still do whatever helps us. That's the same idea as going just up or just down. We had to do that on some problems recently for just straight up and down free fall. All right, some symmetry stuff. Still very similar to free fall. If it takes 2 seconds to reach the peak, how long is it going to take to come back down? 2 seconds. As long as we can assume it comes back down to the same level ground at which it was fired in the first place. That's the same thing we said a few weeks ago when I said, you know, if I throw this up, if it takes 3 seconds to go straight up, it takes 3 to go down. Remember, this is free fall on this axis, so all that stuff still applies. It's nothing new there. I noted again that Vx is constant as long as the air resistance is negligible. And like we've been saying, this is in free fall on the y-axis. So we could use any of those other, I didn't relist the formulas that were given on Monday, because they were the X and Y specific ones. They'll still be used along with these two. Right? These two are irrelevant for horizontally fired projectiles, right? Because there's no angle to start. It just goes this way right off the bat, right? So these are only useful here. Before we jump into the example, I'm just going to draw on this diagram some vector arrows just to represent some of what's there in words on a diagram, like I did on the horizontal one the other day. So, excuse me. Once it is fired, it will have a Vx that is constant. So if the blue line is Vx the whole way through the diagram until after it hits the ground, that vector should be the same length, because remember the length represents the size, right? So if that one's Vx, I'm just going to write it once, not on every one. So the blue is Vx, and showing what we said a minute ago for Vy, it would have on the way up, your Vi gets launched in Vy initial, I should say, Vyi is there, and then as we progress past the initial point on the way up, it should get slower, right? On this diagram right here, if this is the peak, do I draw a Vy arrow to represent it? No, because what did we say it has to be for a moment? It stops. So at that peak, There's no arrow to draw because right there is where we said Vy equals 0, right? And then on the way down it flips and gets faster. There, then there, then there. Right? And there's some other symmetry you could notice. If this, let's throw in some made up time numbers. If this frame is 1 second before the peak, and this frame is 1 second after the peak, there's symmetry in that. So if I was going upward at a Vy of 5 meters per second here, I would be going downward at a Vy of what here? 5 meters per second, right? If it's the same time interval before or after. Same with like this one and this one. That's why I drew these straight across to mention that. Does that make sense to everybody? Okay. And one other really important thing, and it should be listed up here, I just didn't say it yet. There's many times we're going to have to solve for like the whole trip from beginning to end. And this note right here is important for that, because for the entire trip from beginning to end, delta y, the y displacement, is 0. Alright? So that means when I get to this position right here at the end, delta y equals 0. Remember, that just means the y displacement. Remember what we learned about displacement a long time ago, when we first learned the definitions like first week or two of school. Displacement is from where you started to where you what? Ended. Right? So if vertically speaking, not horizontally, if I started at this level right off the ground in this picture and ended on the ground, then I started at where I ended, right? Vertically. I'm not saying horizontally. We definitely didn't end where we started horizontally. We would have a non-zero delta x here, right? And that, so the delta y though, if you come back to where you started, you list as 0. And if you don't remember that in certain situations of certain problems, it'll seem like you're stuck and not have enough information. But speaking of delta x, that would be, if we wanted the horizontal displacement for the whole trip, that's from there to there. And you may see delta x in these problems referred to as the range of the projectile. So I'm going to put that in parentheses. So if it asks, if the problem uses the term find the range of the projectile, that means the delta x for the whole trip from beginning to end. All right? And the only thing I have down here, this is a diagram like I drew on the other one. That's the triangular situation initially. All right? So this really happens right here initially, okay? Where there's an angle that it's fired at. I just took it out and blew it up a little bit so it was easier to draw on. And the V we usually are given, like I said earlier, is that one. And this is where we got to use right off the bat the equations to find Vy initial and Vx. And that's where the sine and cosine ones come from. That would be some other diagram included on that. Alright, so not much more to say about any of that other than getting into an example. So everybody open up to page 151. Yeah. These are just imagine like if we hit the pause button, right, as it's in motion. All right. Now, most problems we're going to do, if not all of them, is going to be from like it will come back down to the same level in this course. Now, like in college physics, AP physics, we do a lot of variations, more than we do in this course. But like, you do have to be careful when you get a little more difficult. Like, if I fire something from this level right here, and it lands like maybe somewhere up here and doesn't come the whole way back down, then I can't say delta y for the whole trip is 0, right? Because it didn't come back to where it started, right? So some of these features, especially that one there, is dependent on the fact that it came back down to that same level. Okay, yeah. Oh, page is 151. Yeah. Yeah, basically. So maybe this will answer your question. So um, let's say we use these two formulas up here to find your Vx and Vyi right away, because we have enough information to. Now let me make up two numbers. Let's say Vx comes out to be 5 meters per second and Vyi comes out to be 8. Okay? So that would mean right off the bat right here, when it's first fired, it's going 5 meters per second that way, 8 meters per second that way. You can use symmetry at the very end. If you know that, if that's truly at the very end, the moment it strikes, then Vx is still 5, because that's a constant. That was 8, I said, right? This would be -8. So if it's in the time frame right across the symmetry of the that term here, parabola, that doesn't make a parabolic shape, it's all symmetry straight across. Does that answer your question? Okay, moving along to, I'm also going to include another part in the example, something they don't ask, but you will often get asked. So they ask for 2 things here. I'll eventually going to put in a 3rd thing at the end. So this is example 1 on page 151. And this is just an example of a projectile fired at an angle. Alright, a ball is launched at 4.5 meters per second at 66 degrees above the horizontal. What are the maximum height and flight time of the ball? Alright, now we still want to do like X and Y column stuff, alright? And it's good to draw yourself a diagram. Since we drew one already or have one here, I'll just flip back to it. So it's just following this same idea here, right? So we got to be real careful though. When it gives you the velocity at an angle, that's not a Vx or a Vy. We got to use those 2 new formulas to turn them into a Vx and a Vy. So I'm just going to list those, not in any like X or Y specific column. This is just a plain old V. It's not on one or the other axis. It's on both of them, so we can't put an X or Y on it yet. Does that make sense to everybody? So it's 4.5 meters per second at an angle of 66 degrees above the horizontal. So really the very first thing you should do, I don't even care what this problem asks, because you can't do anything math with this problem until you get this broken up into Vx, which again is V cosine times the angle. And when you find Vy initial from that through the other formula, which is V sine of the angle. So we plug into both of those, and that's going to be 4.5 cosine 66. Figure out what that is in a second. And this is going to be 4.5 sine of 66. I want everybody to make sure everybody's doing it in your calculators correctly, to pull out or flip over to your Chromebook calculator. You already have it out. And remember, I suggested using the Desmos calculator, making sure it's in degree mode. If it is, on the Desmos one, you could just plug in 4.5, hit the times button, hit cosine, and when you hit cosine on the Desmos one, it starts a set of parentheses to put the angle in. Put the angle in, hit enter, and make sure we all get out the same answers, because sometimes there's an issue with calculators on these. Students on there and use them, and that's going to mess up your whole problem if you can't calculate these correctly right off the bat. Super important, it's in degree mode. If you do it right for the horizontal velocity Vx, it's 1.83 meters per second. And if you do the Vy initial one right, if we round to 2 decimal places, it's 4.11 meters per second. Yeah, everybody get that? We all good? Alright, now that we did that like preliminary step, we could start our listing X column stuff, Y column stuff. Alright? some of this will be included in. So horizontally, of course, we could throw that VX in there now that we kind of extracted it from the original. Can't stress enough, though, that if you try to put 4.5 meters per second in like an X or Y column, you're going to royally mess up. You have to do this and break it into those components first. And really, there's no need anymore after you do these two formulas to accomplish that. There's no need for the angle anywhere in the problem. We have it in the pieces. Now we're looking at it like just the x-axis, just the y-axis, and if we need to bring something together, you can. DYI is that. And just like a lot of things now are just like horizontal projectiles as far as, well, on this axis we're in free fall, right? So we could say G equals negative 9.8 meters per second squared. And as of right now, until we figure out what we're asked, that's all we know, but we got some X stuff and some Y stuff. There'll be some more stuff to fill in there as we keep going along here. Any questions so far? All right, so the first, I know it's not really part A, part B, part C, but they asked us several things, so I'll break it up like that. The first thing it asked us, I'll call part A, is what is the maximum height? All right, let me draw a real super rough diagram here of this thing, just to jot down here. So it's max height. What did we say happens to it vertically? It stops. So for this part, since I'm finding max height, I could say Vy final equals 0. But I could only say that at that position, right guys? Max height. That's when that's true. That occurs right there, right? So if it occurs there, these equations are smart. It knows that if I plug in Vyf is 0, that we're at that position. That's the only place that happens, right? Therefore, if I plug that in and solve for delta y, that will be the max. Because that'll be the delta y right there. Anywhere earlier, it wouldn't be that high. Anywhere after, it wouldn't be that high, right? So in other words, when we're asked to find the max height, you always plug in Vy final is 0 and use the rest of the information to help solve the rest of it, okay? So we find the correct equation. We're looking for delta y at that position, which is the highest position, like we said. So this is going to be, we don't have time, but we don't need it. We should solve this with equation 3, right? The one that doesn't have t in it. So we'll do Vy final squared plus Vy initial, or not plus, sorry, equals Vy initial squared plus 2g delta y. Vy final is 0 at that peak, therefore delta y will equal, subtract over Vy initial squared, and divide by 2 times g. Plug in our numbers, our Vy initial that we found out popped here in our givens was 4.11. Square that, divided by 2 times negative 9.8. We do that correctly and run those numbers. Our Vy initial is 0.86 meters. Your book did it a different way. This is the quickest way to solve for that, though. Your book finds t first and then uses t, which there's nothing wrong with that, but I always try to do it the simplest way. Now t will be necessary though in a later part. That might be why they did it. But sometimes you might only be asked this and nothing else. So if you're only asked for the max height and nothing else, this is the easiest way to do it. Okay? Given those givens like this problem had. Alright? So the most important thing is why it was the max height is because we plug in 0 there. That's the only place the maximum height occurs when that stops at that peak. We okay with that? Alright, parts B are the second thing they asked then. The flight time, it straight up asks for the time next. The flight time of the ball. So, again, drawing just a rough diagram of it. The flight time means from beginning to end, okay? So the whole time from here to here. And what did I say? This is another important feature. When we go from here to here, what did I say delta y is equal to for the whole trip? 0. All right. So we could still use what's above, but are we gonna? We could use the original information. Remember, VYF equals 0 was at this position only, right? Would that apply to part B to find the whole time? No. If we want the easiest way to find the whole time is to, we can still use this. This is all true and good, right? But we're going to use the fact that delta y equals 0 now. So if we use this information here, that is still good because that's still all true from the beginning initially, and use it with this, we could find delta y. We only still need the y stuff. We don't even need the x stuff, right? Only the y stuff. So I have delta y 0. I know Vy initial, I know G. I still need to find T. That's what it'll be, the total flight time from beginning to end. Plugging in that is 0. So that's going to be equation number 2. All right. So that would be delta y is equal to Vy initial T plus 1/2 GT squared. Okay, so remember, it's super important that you follow we're allowed to plug in zeros if anything's 0. Because if you try to solve this without realizing delta y is 0, it's going to seem like you need the quadratic formula, but you don't. Alright, because this is 0, we could divide out a t for the proper algebra here. So pay close attention. I know we've used this equation a ton before. I don't know if we ever used it in this exact way. Alright? So the goal is to solve for t. We do have an issue for a moment. This is a t to the first power, this is the t to the second power. Those can't combine, right? But because this side's conveniently 0, remember we're allowed to do anything in math to equation we want as long as we do it to both sides and every term, right? I could divide out a t. If I divide every term by t, 0 over anything is what, guys? 0. This t cancels out with this t, right? Leaving me with Vy initial. The 1/2 is still there, the g is still there. We know our basic exponent rules. T squared divided by t is what? Just t, right? Now we accomplished getting a t, being able to get a t by itself now, right? There's only a t to the first power. Now we just got to algebraically rearrange it. Everybody with me? So we would subtract Vyi to the other side, multiply by 2, and divide by g. All right. If I subtract Vy initial to this side, then I still have the 1/2. So I multiply that times 2 and divide it by g. That's what the time will equal to. So just be careful with the algebra. I'll just flip it around now. Plug in like this. So 2 negative Vyi. The negative just came from the rearranging. 4.11 divided by negative 9.8. Negatives will cancel. They better because I can't get t's that are negative times. So we'll get 0.84 seconds. So just to recap what we did, first of all, any questions? Let's say that again. No, you can't use the first equation because the way we did it with the givens we had, the first equation has a VF in it. Okay? Vy final. Huh? Yeah, we used the second equation. Alright? Because it has a VYF in it, and we didn't have that as one of our givens. Now, there are alternative ways. So using the least amount of givens, this is probably the best way to do this one. Right? As things get more complicated in physics, especially with kinematic equations, there's often different routes you could go. I will briefly explain some of them. To avoid confusion, I'm only going to do it one way. All right? But this way is really the most typical, best way to go using only givens to figure out the total time from beginning to end of a projectile fired at an angle. One that comes back down to where it started, okay? But listen, you're trying to say use equation 1. Well, equation 1 has VYF in it. Do we have VYF? Now, okay, that's what I'm getting. Yes, you could do that. You didn't say that, but you could do that. I'm going to tell I was just about to tell everybody that anyway. There is an alternative way, all right? What Chris is getting at is the fact that you could choose another way by just finding out how much time it took to go to that peak we found in part A. So we could go back here. If we go, where's my diagram for that? Right here. If we go back to here and still focus on from here to here, because this is what this part of this problem, that's what it cared about, right? Getting that max height. I could use that information, and instead of solving delta y, another thing I could do is solve for t. Now that won't be the total final answer, that's only halfway, right? So if that t came out to be whatever, 0.3 seconds, then the whole time is 0.6 seconds. You'd have to double it if you do it that way. There's nothing wrong with doing it that way if you want to. Alright? But to avoid confusion, I'm going to only do it one way. Alright? If you find another way and it's valid and your work backs it up, I'm completely okay with that. Because that can happen. There could be alternative ways to do the situation. But one of the biggest reasons I picked this way to do part B is because if you had a problem that only gave you the same information and only asked you part B, this is the best way to do it because you don't have to worry about anything else that you found or were into in another part of the problem. All right, and that's why I chose showing it like this. All right, but this way is dependent on realizing that delta y for the whole trip was 0. If you don't realize that, you're going to be stuck trying to use this equation. Any other questions? All right, there's something they don't ask. It's going to be very simple, but you will often be asked this, so I'm going to include a part C. It didn't ask me anything about the horizontal axis, did it? Now we know Vx right off the bat, but I want to find, if it says find the range or the horizontal displacement for the whole trip, that's what I want to ask you. Remember what the range was? Delta x, right? If I say the term range, that means definitely for the whole trip. So that means find delta x. We have everything, we just got to put it together. What's the only equation we have for that? Vx times what? T. We have both of those things already, right? We just got to go back and find them. Delta x was, or Vx, excuse me. What was it? Way back here. 1.83. And now we use the total time, which we already found in part B, right? 1.83 times 0.84. That'll find out how far it went from beginning to end horizontally when fired at this angle. So 1.83 times 0.84 is going to be about 1.54 meters. That's an easy thing at that point, especially once you have all that stuff. Now, if the problem just said find the range right away, you would need to realize I need to find t even if they don't ask me, right? But pretty much, if you could follow the 3 pieces of this problem, not every projectile problem is going to ask you all 3 of these things. Some might, some will only ask you parts of these. But if you could do any one of these parts, you should be fine on any projectile at an angle problem you come across that I give you. All right? I'll give you a couple for homework. What we're going to do is go over them tomorrow. There's going to be Friday, the day you guys aren't here, you're going to get assigned concept builders on both types of projectiles. I'll also assign tomorrow something, it won't be due till next week, but a set of review problems, like a handful more of mixed types, both since we now have 2 types. But that won't be due till a later time, sometime later next week. Yeah, we'll have to do early. So homework on this stuff is going to be page 152. It's going to be 4, 5, and 9. 9's down at the bottom. Before we do anything else tomorrow, we'll go over questions with those if we have to. So really follow the example, because these are very, very similar to the example. Everyone, stop there. You got a couple minutes to start if you want to right now.